All right, everyone. So as engineers, we love our simplifying assumptions, right? It just makes the math work. We often look at a block of steel and treat it as perfectly uniform, the same in every single direction. But what if I told you that assumption isn't just a little bit off? It can be catastrophically wrong. Today, we're going to pull back the curtain on the hidden, directional nature of materials.
So let's kick things off with a question that should really make you stop and think. How is it possible for a single solid piece of iron to be more than twice as stiff and strong when you pull on it one way compared to another? I mean, think about that for a second. It's the exact same piece of metal. This isn't a trick question, folks. The answer has massive implications for how we design pretty much everything, from bridges to jet engines.
And here's the cold, hard data. This is what I'm talking about. If you measure the elastic modulus, which is just a fancy term for a material's stiffness, along the edge of an iron crystal, you get a pretty respectable 125 gigapascals. But if you measure that exact same crystal along its main diagonal, that value just skyrockets to 273 gigapascals. That is more than double. This isn't some fluke. It's a fundamental property of the material itself.
So the answer to our little puzzle has a name. Anisotropy. It's a simple but really profound idea that a material's properties can completely change depending on the direction you measure them. Now, to understand why this happens, we need to forget the big macro-level picture for a minute and zoom way, way in. I'm talking down to the world of individual atoms.
Okay, so how do we even start to get our heads around this directional behavior? We have to think small. No, I mean atomically small. We need to find the basic building block of these materials, that fundamental pattern that repeats itself over and over and over again to create the entire structure.
And this is it. It's called a unit cell. The best way to think of it is like a single perfect Lego brick that you can use to build an entire castle. It's the smallest possible repeating arrangement of atoms that captures the entire structure of the crystal. If you can understand this one little cube, you can understand the whole material. It's that fundamental.
Now, to talk about all the different directions and planes inside this tiny atomic grid, we can't just point and say, that way. We need a precise universal language. And for crystallographers and material scientists, that language is called Miller indices.
Think of it like a coordinate system, like a GPS for the crystal's internal structure. It's a pretty clever three-step process. First, you just find where a plane cuts through the X, Y, and Z axes. Simple enough. Step 2, and this is the really clever part, you take the reciprocal of those numbers. Now, why would we do that? Well, it handles planes that are parallel to an axis, because their intercept is technically at infinity. And what's the reciprocal of infinity? 0. It gives us a nice clean number to work with. Finally, you just pop those numbers into parentheses, and boom, you've got your Miller index. It's a perfect address for any plane inside that crystal.
And here's a perfect example of what that looks like. This specific plane is called the 111 plane. So why? Well, it runs parallel to the x-axis, its intercept is at infinity, so that first number becomes a 0. Then it cuts the y-axis at the 1 mark and the z-axis at the 1 mark. See? 0, 1, 1. It's actually pretty simple when you break it down. And now we have a precise name for this exact slice, which is the first step toward predicting how it's going to behave.
Okay, let's build on that. Because not all of these unit cells are built the same way. Nature has a few favorite blueprints it uses to arrange atoms. And for most of the metals you're going to run into as an engineer, it really just comes down to two main designs. Over on the left, we have the body-centered cubic structure. We just call it BCC. It's got an atom at each corner and one single atom right in the center of the body. Now on the right, you see the face-centered cubic, or FCC. This one has atoms at the corners, sure, but also in the middle of each of its 6 faces. They look pretty similar, but trust me, that one little difference in where the atoms are placed, it changes everything. And just look at how that small architectural difference leads to some big changes in properties. The FCC structure is way more densely packed. Each atom has 12 immediate neighbors, which we call its coordination number. Compare that to only 8 neighbors in a BCC structure. And check out the examples. Your ductile, easy-to-form metals like aluminum and copper, they're FCC. But the strong, harder metals like tungsten and, this is the important one for our puzzle, iron, they're BCC. And believe me, that is not a coincidence. Okay, so we've got our building blocks, the unit cells, and we've got the blueprints, BCC and FCC. So now for the crucial part. How does all this atomic architecture finally solve our puzzle? How does it explain why that piece of iron was so much stronger in one direction?
Well, it all comes down to this concept right here, linear density. And put simply, it's just a measure of how tightly packed the atoms are along a specific line or direction within the crystal. If you draw a straight line from one point to another, how many atoms do you literally run into? That right there is linear density.
And this, right here, is the key takeaway for today. In a BCC crystal like iron, the atoms are not evenly spaced out. If you travel along the edge of that cube, the atoms are actually pretty far apart. That's a low-density direction. But now, imagine traveling along the body diagonal, from one corner straight through that center atom to the opposite corner. What do you see? The atoms are packed shoulder to shoulder. This high-density direction is inherently stronger, inherently stiffer. That tiny packing difference, on an atomic level, is what creates the massive strength difference we can actually measure on a human scale. And just like that, we've solved the puzzle.
So, I'll leave you with a design challenge, because understanding anisotropy isn't just for an exam. This is real-world engineering. Imagine a jet engine turbine blade spinning thousands of times a minute. The centrifugal force is immense, and it's pulling straight out along the blade's length. Knowing what you know now, how would you want to orient the iron crystals inside that blade? You'd want to align that strong, high-density diagonal direction with the direction of the greatest stress. Answering that question correctly is the difference between a safe engine and a catastrophic failure. It's how we engineer things that are not just strong, but built to last.